Welcome back. So we're going to continue with an example. Okay. So this is an interesting example. So first follow the blue parts. Okay. There's a problem here. A reward function is R. Okay. So this R depends on your control variable CT and your state variable ST. Okay. What is different about this problem is that your control variable and your state variable are defined in discrete sets. Okay, so they are not continuous variables. So your reward function is also not continuous. Okay, so it is not. I mean, even if the function could be written in a continuous way, it is not differentiable in these points, at these points. Okay. Instead, we have something like this. All right. So if you are in state S, okay, state S could be either A or B. All right. You may imagine that this is good weather or bad weather. Then X and Y are your control variables. So the values for your control variable. So if you are at state S, and if you choose C, your reward is RCS. Okay, and then there are, of course, 4 values only, right? And these 4 values are assumed to satisfy this inequality. All right. So at state A, the reward you get by choosing control Y is the largest. Then the second largest is state B, control X. Then the third largest is the state B, control Y. And the lowest level, which is still greater than 0, is that in state A, you choose X. Okay. Then there's, of course, a transition equation. And here, for simplicity, the transition equation depends only on your control. Okay. So if at period T you choose X, your state is equal to A in the next period. Okay. If at T you choose Y, the otherwise condition here, your state is equal to B in the next period. Okay. Then you have 2 options, right? If you think simplistically, if you want to find a non-stochastic policy function that depends only the state, right? This is what we are looking for, right? As always. So we want to find a policy function that depends only on state. Then you have 2 options, either policy function 1 or policy function 2, right? Because these are basically reverse, right? In the policy function 1, the green one, you choose Y if state is A, and you choose X if state is B. In the other one, in the red version, in policy function 2, you have CT equals X if ST equals A. All right. Now, of course, the question is how to solve this problem. So it is not differentiable. So the first order condition and the envelope condition are not well defined. You cannot take derivatives. So there must be another way to attack this problem. And that other way, since the state space is very small, right? The state space is small. You only have 2 values. Then you can calculate everything because you already know what these rewards are, right? So you can try policy function iteration. I will show you very briefly, okay, how you can use policy function iteration here. Now, obviously, in the initial step, right, you want to choose a policy function. Let's say you choose this. So CT equals that. Otherwise, right? Then you're going to understand the transition. Remember, the transition tells you that ST plus 1 will be equal to A if CT is equal to what? If CT is equal to X, and it will be equal to B otherwise. Okay. Now you can understand the rewards and the controls, right? According to this policy function, suppose that S0 is equal to A, right? If S0 is equal to A, C0 will be equal to what? X. If C0 is equal to X, S1 will be equal to A, right? Then C1 will be again X, all right? So that goes on. So there's no change in the state under this policy function, right? And no change in control. Then you realize the rewards are always RXA, right? RXA here, RXA here, RXA here, and that goes on like this. So the value, if you start at S0 equals A, your value is like RXA plus beta RXA plus beta square RXA, right? That goes on. So at the end, you have RXA 1 minus beta, right? So similarly, if you have S0 equals B, now what happens? Now if S0 is equal to B, C0 will be Y. Okay, if C0 is Y, S1 will be equal to B. If S1 is equal to B, look at the policy function. The policy function tells you that C1 is equal to Y, and again, that goes on. So this will tell you that if S0 is equal to B, then you will have R YB divided by 1 minus beta, right? So that was one policy function. Now, how do you write V1, right? You want to write this because this is now you're going to continue. You're going to update your Bellman equation, right? So you want to write V1. So V1 will be what? You are getting RXA in the case of A. You are getting RXA in the current period, right? Then you're going to get B V0, right? But you should be realizing that, where's this? Okay. So now you want to choose which policy to adapt in the second period, right? Because now you have this. So in the second period, you want to find a policy function that maximizes that, right? So you have if ST is equal to A and CT is equal to X, you have what? VA RXA plus beta beta RXA divided by 1 minus beta. This is your V1, sorry, V0, right? And if the state is A, if you choose CT equals Y, you have RYA plus beta, again, RXA, 1 minus beta. Okay? Now, which one maximizes your V1? So this is your V1. Right? Which choice maximizes V1 if the state is A? Okay? You're gonna find that and you're gonna realize this says CT must be equal to Y because we assume that RYA is greater than RXA. Then your V1A will be equal to what? RYA plus beta RXA 1 minus beta, okay? So if you do the same with B, okay, with ST equal B, then CT equal X, CT equal Y, you're gonna try these things and you're gonna realize this tells you that CT must be equal to X in this case because Rxb greater than Ryb, all right? So V1b will be equal to Rxb plus beta Ryb1 minus beta, all right? Now you're gonna check your policy functions converge, right? So this is your second step. What was the thing that we assumed? We assumed that Ct equals X if state is A. Now we are comparing whether these policy functions are the same, right? First iterate and the second iterate. So it says Ct equals X if St equals A. So we look at what we found here. It tells the reverse, right? So there is no convergence in the first step, okay? Then you're gonna go to the second step, okay? And in the second step, if you do the same, you're gonna realize that there is a policy function. So I'm not gonna do that, but you should do it. So you're gonna realize the policy function that works, that converges, is this. Okay, so this is, I guess, the red one. So then your policy function iteration concludes that this must be the policy function, right? But you should also check one thing, right? Starting from any state, you should also check whether VA, so whether S0 under this policy, okay, so there is always this alternative policy, right? The green one in this case. So you're gonna find, let's say, green and red, all right? So you must be sure that this is satisfied, okay? Because there is no envelope condition here, right? There is no derivative, so you must be sure, you must ensure that this is true. And that will require further inequalities between these rewards, okay? XA and XB, okay? And these rewards require, these inequalities are, if you solve them, for each state, you will have this. You will have RYA minus RXA plus beta RXB minus RYA plus beta square RXA RXB greater than 0. And for the other state, you will have RXB RYB plus beta RYA RXB plus beta square RYB minus RYA greater than 0. Okay, so let me check. YXA, XB, YA, XA, XB, okay, XB, YB, YA, XB, YB, YA. Okay, so then for this to be true, these also must be satisfied, okay? Because let me find the red policy again. So the red policy is sorry. So the green policy will be correct. Like, sorry, this was wrong. Okay. So this is your green policy, and green policy will maximize. So here we are looking at strict inequality because these inequalities are strict. So it doesn't really matter. I mean, if you find these things, it is already good enough. Okay, so where's that? I don't want to. Okay. All right. So, any questions about this? So, as you see, policy function works, but you have to check whether it is really the solution because there is no envelope condition here. Okay. All right. If you do not have any questions about all this, I want to show you how the stochastic versions would look like. How do we approach the stochastic problems? So let me continue then. You can stop me anytime for questions and clarifications. All right. So let's go back to our optimal growth problem, right? So I have the production function, right? And consumption and capital stock.
Can you share your screen?
Oh, okay. Sorry, I forgot that. Thank you. Right. So this is the simple problem that we studied before. So alpha is between 0 and 1, lambda is greater than 0. Then we have this utility function, which is logarithmic, right? And the purpose is to maximize this stuff, right? There's the discount factor, and then CT, t goes to positive infinity. We want to maximize this by choosing a sequence of consumption levels by meeting the constraints, obviously, right? And beta is, again, between 0 and 1, all right? Now, this problem, of course, is deterministic, right? Because when I choose KT, I know exactly how much, I mean, when I choose KT plus 1 and CT, I know exactly how much output I will have in the next period, right? Now, suppose that is not true. Suppose that there is a technology shock, all right? And let me use this formulation. Now, ZT here will follow any probability distribution, really, right? I mean, that could be many different, there could be many different probability distributions. For instance, you can tell me that ZT is an independently and identically distributed normal variable with 0 mean and constant variance. So that would be one possibility. Another possibility would be an autoregressive form, such as this one. Okay, now epsilon t would be a standard normal variable. Okay, now obviously, if rho is equal to 0, they are the same, right? If rho is equal to 0, they are the same. But once we introduce the stochastic element here, then the problem must be written in this way. Okay, so E0 here is the expectation operator. Okay, so this means if I want to form the expectation of a variable, all right, I'm taking the expectation of this by using all the information I have in period 0. Okay, so I0 here is the information set. Okay, so this expectation will be conditional on what the decision maker knows about the economy information. You know, this is the entire set of information about the economy, about the shocks, etc. All right. For instance, at 0, you don't know anything about epsilon 1, right? You only know the distribution, but you don't know the realization of it, okay? So let's first imagine how we can write the Bellman equation, right? Now, obviously, we have two state variables, right? One is KT, as is typical. This is the capital stock. And this is my now endogenous state. Now, there's a difference between endogenous state variables and exogenous state variables. Okay? Then again, I will have this thing maximized. So I have ln CT plus beta. Now careful, the continuation value at T will be written only in expected value terms. Right? Because I do not know epsilon T plus 1. All right? So your KT plus 1 will be equal to e to the ZT e to the ZT lambda KT alpha minus CT, all right? But the continuation value will depend on ZT plus 1, and ZT plus 1 depends on epsilon T plus 1. Okay, and epsilon T plus 1 is a standard normal. Okay. Now, there are a couple of things you can do depending on the model you have. One thing is the perturbation method, right? You're gonna take the first of the conditions, and then you're gonna have a dynamical system that is now stochastic because of this again, right? Because of this again, it will be stochastic. Or you can try guess and verify. I will show you how you can do that. Let me find my stuff. Oh, by the way, of course, you realize this expectation is now conditional on information you have at T, right? So in principle, you have this probability of ZT plus 1 less than some Z conditional on ZT. So what is that? So this is basically this CDF, right? The cumulative distribution function, right? So now, since this probability will be conditional on ZT, you can actually write this in this way, right? So you have rho ZT plus sigma epsilon T plus 1 less than Z conditional on ZT, okay? So you have this event is like this, sigma epsilon T plus 1 is less than Z minus rho ZT conditional on ZT, okay? So this probability is then equal to what? Epsilon T plus 1 is less than Z minus rho ZT divided by sigma, conditional on ZT. Now realize that you already know this, right? You already know this CDF. This is standard normal. So you basically take the, you basically normalize, okay? So this is very practical. You normalize your Z using this, okay? That is very useful in practice. In the numerical work, you're going to use such things. So again, guess and verify will work. I will show you how you do that. Maybe I can first show how to use guess and verify. Okay, so remember the guess and verify method. We first choose a particular value function, right? And then we solve the problem. We write the we solve the problem by writing this, okay? And then we check whether it is true or not, right? So how can you do that? Let's say the guess is this. Let's say you have a constant here, okay? Then you have that, as in the earlier case. So that was the earlier deterministic version, right? Now there appears to have to be a ZT here, and I'm putting this linearly. Why? Look at your production function. Your production function is like this. So if you take the natural logarithm, z goes linearly, right? So if you take the logarithm here, you have ln lambda alpha ln kt plus zt, right? So then I put a linear term here as a function of zt, right? Then I have kt plus 1, zt plus 1, which is equal to that, right? Now be careful, you're interested in the expected value of this. Now this expectation will be written in this way. Careful, it is expectation of V conditional on information you have at t, right? So it is phi plus omega ln kt plus 1. Careful, you are choosing kt plus 1, so you know what it is, all right? But be careful here, you must have et zt plus 1, okay? Now what is et zt plus 1? Et zt plus 1 is expectation of rho zt plus sigma epsilon t plus 1 conditional on zt. So you have rho zt plus expected value of that, and this is equal to rho zt, right? Because e epsilon t plus 1 is equal to 0, right? So if you do this, it works. I'm not going to do that. You know how it works. You should do it. At the end, you're going to find this solution. Let me find the solution. So it's a bit long, obviously, but at the end, you're going to have something like this. If I am not wrong, you should double check. Maybe I have a mistake. That can always happen. So omega will be that. Lambda will be what? Alpha beta divided by 1 minus alpha beta, 1 minus beta rho. And phi will be this long thing, 1 over 1 minus beta, natural logarithm of lambda 1 over omega plus beta omega, natural logarithm of lambda omega 1 plus omega. Okay, so you should check this. Okay, where am I? Okay, I want to discuss this right now. Okay, there's that. That's here. Okay. Now, in practice, obviously, in practice, you will have something like this. Suppose that you want to apply projection-based methods. Okay? So you need to discretize your state space, right? Now, your value function has 2 arguments, okay? And you want to find a way to write a grid. Okay, the grid will be like now, like this. Sorry. So your grid will be like this, right? So this is KT, let's say this is ZT. And you want to look at this area. Right? There are many points. So for each of these points, there's a particular K and particular Z, right? That goes on like this. Now, if you do it well, so there's always the question of how fine should it be? And that depends on your computing power, that depends on the precision you want to have, etc., right? But suppose this. Suppose that there is this set such that you can write your possible values of Z in this way, right? Now, one thing you can do is to directly specify the Markov transition probability matrices. Okay, so what are these things? Very simple. You want to have this. So in state ZT and in states ZT plus 1, there must be a transition law from T to T plus 1. Okay? There will be a transition. Suppose that there are now 3 values. Okay? Z1, Z2, Z3, Z1, Z2, Z3. Okay? So if your state is ZT today, you want to know this probability. It will be equal to Zj conditional on Zt is equal to Zi. Okay? All right, so let's denote these probabilities by Pij. Okay, so you have what? P11 here, P12 here, P13 here. You have P21, P22, P23, and you have P31, P32, P33. So what is this? Look at this, for instance. So this is the probability that if you are at Z2 today, okay, if you're at Z2 today, this is the probability that you're going to be Z1 tomorrow. Okay, so the second row, first column. Okay, now in general, of course, we assume that this is true. So each of these probabilities are between 0 and 1, but you should be careful one thing here. The row sums must be equal to 1, right? In each row, these must be equal to 1. In each row, these probabilities must sum to 1. Okay? So now then you can write, right? Then you can write your this, right? Because now you know what's the probability of being at Zj conditional on you are at Zi. So you can actually calculate for each K, obviously. For each K, you can calculate what this probability is. Okay? you understand. So if you want to do the perturbation method, it's also very simple. In the case of perturbation method, you write the Bellman equation in the typical way. Okay. You write your Bellman equation in the typical way. Then you take the first order condition with respect to your state variable, right? So now be careful. You are also evaluating this derivative by the information you have at t, okay? Then the derivative of kt plus 1 with respect to ct will be equal to -1, as always. Then you will have the envelope condition for the endogenous state variable, obviously, right? So you are gonna have vk, kt, zt. Notice that I'm not writing any expectation operator here because this is what you know at t, okay? Then you're gonna have beta, again expectation, vk, kt plus 1, zt plus 1. Then you're gonna have alpha, lambda kt alpha minus 1 e to the zt. Okay. Then you also have the, of course, the constraint. Okay, so you have e to the zt lambda kt alpha minus ct. Now again, you're gonna have a three variable dynamical system. Okay, we have less than 1 minute, so let's meet at 2:50. All right, we're gonna continue. You're gonna hear me? All right. All right. Let's
Yes,
meet
okay.
at 2:50.